So this conclusion means that F is locally surjective. Why B is an interior point means locally surjective. So here is B. This is the image F omega. B is an interior point means that a small neighborhood of B, epsilon small enough, then this ball, the epsilon neighborhood of B, will contain in the image. That is, every point near B is a point in the image. Okay, so this is the reason why we call such property locally surjective. Okay, it is reasonable to call such property as locally surjective. Therefore, this theorem means that if the linearization of F at the point A is surjective, then F itself is locally surjective. Okay, and our inverse function theorem says that if the linearization is invertible, then F is locally invertible. Now we have this locally surjectivity theorem. Of course, you can consider the case that if the linearization is injective, can F be locally injective? And what locally injective means? This is an interesting question. You can try to solve this question. Solve this problem. I will not include this problem into our course because due to the time limit. Okay. Now, how to prove this theorem? We will apply the inverse function theorem to get our result here. But the inverse function theorem concerns maps from maps between the same dimensional Euclidean space. For the inverse function theorem, the domain of definition and the target domain should be target space should have the same dimension. But now our map is a map between Euclidean space which is different dimension. So how to prove this? So the only way is that we use our map F to construct a new map between Euclidean spaces of the same dimension, so that we can apply the inverse function theorem to the new maps. Okay, so we F is a map into Rm. Therefore, the map F has m coordinates, m components. So we write F to be F1, Fm. F1, Fm are the components of our map F. Then, the condition that the rank of the Jacobian matrix or the rank of the determinant derivative is m. So the Jacobian determinant we write here. F prime A is D1 F1. Or we use the simpler notation F11. Fij is Dj Fi. So F11 F1 M F1 m plus 1 F1 n Fm1 Fmm plus 1 Fmn. Okay, all the derivatives are taken at the point A. Okay, the rank, the derivative is m by a matrix. The rank is m. Therefore, n will not less than m. M may equal to m or greater than m, but n will never less than m. So the derivative matrix or the derivative f prime a must of this form. So the rank is m. Therefore, we can there is determinant contained nth order determinant contained in this matrix, which is not zero. So we might assume, without loss of generality, we might assume that this determinant, the determinant of this matrix, is not zero. We might make this assumption. In other words, we might assume that the first n columns of this matrix is linearly independent. Okay, the rank is n, so there are n columns which are linearly independent. Without loss of generality, we assume that the first n columns are linearly independent. Okay, so we assume without loss of generality, we assume the determinant of Fij is not zero. Here ij 1 to m. This is n by n matrix. N by n determinant is not zero. So we make this assumption. Then, as I said before, we need to construct a map from Rn to Rn. We need to construct a map between Euclidean space of the same dimension, so that we can apply the inverse function theorem. Now, the map should related to our given maps F here. So the map we denote by phi. Define a new map from omega to Rn. Defined by phi x is fx x n plus 1 minus p n plus 1 xn minus pn. Here, no p, maybe a. Sorry. Yes. A n plus 1 xn minus an. Here, x is x1 xn plus 1 xn. Okay, and also a is a1 an. Okay, so we define this map. This map is from omega to Rn, because the right hand side has n components. Why? Because F has m components. Now we add the other n minus m components here. So altogether, phi x has n components. Therefore, such a phi is a map from omega to Rn. Okay. Now, having defined a map between space of the same dimensions, where we compute phi a. Phi a is fa, and the other components are zero, right? When x equal to a, the last n minus m components of phi x is 0. So phi a is fa 0, and we compute the derivative of phi a. Phi point a. What's phi point a? Phi point a. Phi point a is the coordinate of phi is f1 fm xm plus 1 minus am plus 1 xn minus an. So the derivative of phi at the point A, or the Jacobian matrix of phi at the point A, is the derivative of all the components of phi which respect to x1, x2 until xn. Okay. Therefore, firstly, the first row of this matrix of the derivative matrix of phi A is the derivative of f1, which respect to x1, x2, xm, xm plus 1 until xn. So this is f11 f1 m plus 1 f1n. This is the first row of phi point A, and until the mth row. The mth row is the partial derivative of the m's coordinate of phi, fm. Therefore, the nth row is fm1, fmm plus 1, fmn. Now the m plus 1 is this m plus 1 coordinate, the derivative of the m plus 1 coordinate with respect to x1, x2, xm plus 1 until xm. But this coordinate, the m plus 1 coordinate of phi, does not depend on x1, x2, xm. It only depends on xm plus 1. Okay, therefore the derivative is 0. Now this position is the derivative of the m plus 1 coordinate of phi with respect to xm plus 1. That is 1 here. Okay, so here we get 1 here. The other components are 0. Similarly, the other are 0 and 1 here. The last row of the matrix is the partial derivative of the last component of phi, that is xn minus an, with respect to x1, x2, xn. But only the derivative, the last derivative, with respect to xn is 1 here. The other derivative are 0. Okay, so in this manner, we have to compute the derivative metric of our map phi at the point A. But now we look at this matrix closely. Here is a 0 block here, and this block is the n minus m identity matrix. And now the upper left corner of this block of this matrix is no singular. The determinant is not 0. So our phi point A is a matrix of the form. This is no singular. How to write? Say A. A is no singular. And this is a matrix we don't care. And this is 0. This is the identity matrix. So the matrix is of this form. Because this A, that is A here, A is invertible. So we conclude that the derivative of phi at our point small a is invertible. So we can apply the inverse function to phi and say something.